When we eat energy-rich foods like fat, carbohydrates, and proteins, those fuels get oxidized and converted into a form of energy in the cell called ATP. And ATP is said to be the energy currency of the cell, but you might wonder, why can't we just use the energy that's in the food that we eat? To understand this, let's think about what happens if we don't have a common currency. For instance, let's say you grew wheat in a field and you were able to turn it into flour, but you didn't have a way to make pizza or anything else. So you would go to the pizza shop with your flour and they would say, okay, we need flour to make pizza, so we'll give you some pizza for food. But now let's say you also needed some shoes because when you're out in the field, you needed to protect your feet. And when you go to the shoe shop with the flour, they say, I'm sorry, we can't use that flour. You'll have to not get any shoes. On the other hand, if you went with money that they could use then to buy things for shoes, you could buy the shoes. So ATP is like a currency. And the reason it's an energy currency is because when it gets hydrolyzed to ADP plus inorganic phosphate, it releases energy, and that energy, the ATP, can be used by many different proteins in the cell to do work, and that work can be movement. So when you move actin and myosin, that uses the energy of ATP hydrolysis, or solute transport if you want to move sodium out of the cell. That takes energy and it can use ATP to do that. Or you can use that energy for signaling between cells to tell them what to do, or to make new biomolecules, so biosynthesis. So that energy of ATP can be used by many different proteins in the cell. It's a common currency. And when you hydrolyze ATP, you give off free energy, so it's a very favorable reaction. The delta G naught is minus 7.3 kcals per mole. It's exergonic, meaning it's favorable. But if you wanted to make ATP, that would be unfavorable. You would need to put energy into that reaction. This is endergonic. Because the opposite reaction has a delta G naught of plus 7.3 kcals per mole. And to put energy into that, that's what it means when it's endergonic. You can't make the reaction go unless you do some work. And that energy comes from fuel oxidation in animals. And that is a process called catabolism. And just to help you appreciate how much ATP is being used in the cell, we only have at any one time about 100 grams of ATP in our body, but on a daily basis we make 40 kilograms of ATP a day. So ATP is the energy currency of the cell. And to understand where that energy comes from, let's look at the structure of ATP shown here, where you have an adenine base attached to a 5-carbon sugar ribose and 3 phosphoryl groups that have these 3 high-energy phosphate bonds. ATP is this entire molecule called adenosine triphosphate. If you remove one phosphate group, you have adenosine diphosphate, and if you remove the third one, you have adenosine monophosphate, AMP, ADP, and ATP. Now, to see where the energy comes from, if we take off one phosphate group, we have an inorganic phosphate group, and it's negatively charged, but it can have a resonance structure that spreads out that charge and allows it to interact more favorably with water. And then over here So this is inorganic phosphate. And over here you have the ADP molecule, which also can have some resonance to spread out those two negative charges, and that helps to stabilize it. So this means that ATP hydrolyzing to ADP in inorganic phosphate is very favorable. And of course, you start out at pH 7 with all these negative charges here, which are unfavorable to have. So that's the basis for the large change in free energy when you hydrolyze ATP to ADP. To understand how you can use this energy, let's look at the free energy of some compounds that have phosphate groups. Here is ATP with its standard free energy of minus 7.3 kcal per mole. And that's a very favorable reaction, and so that means that it could take that phosphate group and favorably donate it to glucose to form glucose 6-phosphate. If you remember from the lecture on free energy, this energy can be added, and so that can make it favorable. And if you don't understand this, take a minute to write out these reactions and convince yourself that when you couple ATP hydrolysis to the formation of glucose 6-phosphate, it's a favorable reaction. The other thing you should notice is that phosphoenolpyruvate, or PEP, has a very large favorable free energy when it loses its phosphate group. This compound can be used to make ATP in the cell. And the same is true for 1,3-bisphosphoglycerate, which we call BPG. And you'll see that come up in glycolysis. So let's summarize what we learned. We learned that ATP is the energy currency of the cell, and that its hydrolysis is a very exergonic reaction. And there are properties of the ATP molecule, the phosphate bonds, that make this reaction favorable. And then we learned that there are other phosphate-containing compounds, like phosphoenolpyruvate, which are even more favorable than the hydrolysis of ATP. And these compounds can be used to make ATP.